Welcome folks. I'm going to start this lesson just by asking a simple question. And that question is, what connects these two objects? Now, if you said, took the easy option and you said physics, of course you'd be correct. But there's something far more interesting which lies beneath that in physics, which connects these two objects. And it is the concept called resonance. Now, we've already discussed what resonance is, but we're going to review that and go back on it in this lesson. Put simply, resonance is the ability of a material to vibrate at its own natural frequency. Now, that frequency is dependent on a couple of different factors: the material itself, the length of the material, etc. And in fact, humans, the human body has its own natural resonance and frequency, around 5 hertz, and Earth also has its own natural frequency, around 7 or 8 hertz. It's called Schumann resonance. Definitely worth looking up. The whole principle of musical instruments is based on resonance. The ability of these panpipes to resonate, vibrate at a certain frequency, is dependent on the actual length of the pipe. And that's why we see this beautiful curve associated with panpipes, because it ties back into a different set of frequencies. So today's lesson is going to focus on a specific type of resonance, and that is called open air column resonance. Now, there are two things that we need to talk about before we go on. So just some definitions to take care of. When we talk about open air column resonance, just to recap, objects tend to vibrate at natural frequencies, and these are called resonant frequencies or harmonic frequencies. If both ends of a tube are open, so we're talking about a musical instrument here, if both ends of a tube are open, a musical instrument is said to contain an open end column. For example, a flute and a recorder. So that means that the end here, if we look at the flat instrument, the tube on a horizontal, there's an open end here and here. So it's got an open end. Of course, not all woodwind instruments are open on both ends, but if they are, we say that it's an open end, open air column. So what happens in an open air column? Well, the important thing to note is that air is actually free to vibrate at the open end of the air column. So the air is actually free to vibrate back and forth, move back and forth, and so on at the open end. If that end of the column was closed, the air molecules would be trapped and wouldn't be free to vibrate. So what does that look like? Well, when we draw standing wave patterns, and standing wave patterns are the patterns that are drawn for these particular harmonics. We use standing wave patterns and to show these harmonics. And what's the value of standing wave? Well, standing wave patterns show a wave coming in and then a wave going in the opposite direction. And what you tend to see is, you see when these frequencies are hit, you'll see that the wave actually appears to be motionless, and that is there's periods of big displacement, and we call these antinodes, and there is parts of it where there is, I'm just going to do this in a different color, where there is minimal displacement, and these are called nodes. So in a standing wave pattern, you get a collection of antinodes and nodes. So if we just go back here, if the air is free to vibrate, and we're going to draw this in a standing wave pattern, what we would expect to see is we would expect to see maximum displacement at the ends, because the air is free to vibrate and allowed to vibrate. Now, what happens in between that? Well, we know that we're going to have some sort of a pattern like this, and the different patterns, the different wavelengths that can be achieved within that column are called harmonics, and we're going to have a look at the different patterns that can be done. But for now, it's important to note that if the column is open on both ends, what we're going to see with that standing wave pattern is we're going to see an antinode. So what are harmonics? The musically inclined amongst you will already have heard this term many times. Harmonics, standing wave patterns and resonance is only observed for material at certain frequencies. These special frequencies are called harmonic frequencies, or just simply harmonics. So for an open air column, remember that we have maximum displacement at the ends of the column, and we show that with an open wave pattern, a standing wave pattern rather, as an antinode. Now, if we want to figure out the relationship between the length of the open air column and what the wavelength looks like, we need to run through these set of frequencies. So the first frequency, the first harmonic frequency for which we'll get resonance and a louder sound, if you like, in that tube, is called, the first harmonic is called the fundamental frequency. It is the lowest frequency for which resonance will be hit at that particular length of tube. And because it's the lowest frequency, it is the highest wavelength that can be achieved. Now, I always think it is a good practice to actually draw out a typical wave pattern on the side when you're doing these harmonic setups, because it may help you just to visualize the different wavelengths and different harmonics. So if we're looking for the first harmonic, which is the lowest frequency, the highest wavelength that can be squeezed into this particular tube, remembering that we have an open pattern here, so one end of the tube would have to be here. Well, then the highest wavelength, the biggest wavelength that can be achieved, is when we just hit the next maximum displacement pattern. So in other words, here. So we traverse from this point to this point. And so let's see what that looks like. It's going to look a little bit like this. So when we talk about that, for the length of tube that we've got, what we've actually drawn out in this case is we have a relationship between the length of the tube and the wavelength that fit within it. Now this red wavelength in this length of tube, if we go back to this pattern here and we have a look at it, we should hopefully be able to see that that's a half a wavelength. So it's very important for an open-ended column. There's a relationship between for all of these rather, there's a relationship between the length and the wavelength. And the first harmonic for an open-ended column, the length of the tube is equal to half the wavelength, or another way of writing it is that the wavelength is equal to twice the length of the tube. Now that is the biggest wavelength that we're going to see, the lowest frequency, and so it's called the fundamental frequency, the first harmonic. So if we go chasing for the second harmonic, again, on the right hand side, I like to draw a wavelength here just so I can visualize this. And I'm going to look for, set one of my open ends here. This time I'm not going to choose this open-ended column. That would be the first harmonic. I'm going to go and look for the second period of maximum displacement, second portion of maximum displacement. So it would be over there. And my goal now is to try and fit this pattern into this column. So we've got the first one, and we're going to fit this pattern in the green into this. So we go down. That would be my first harmonic, of course, but we're chasing the second harmonic. So the second harmonic is going to look like that. Now, sometimes you're going to see this represented as a standing wave. So I'm just going to start putting this in. And what this basically means is if there was a return wave, it would look something like this. So it's going to be in the opposite direction. So what we're looking at here is the second harmonic. And again, some important things to note. We have an open-ended structure, open-ended column. So we have maximum displacement. Now we've got to have a look at the relationship between the length and the wavelength. So for this second harmonic, we see that the length is equal to, and now if we look at the green pattern over here between here and here, what we've actually got is a full wavelength. So the second harmonic, for the second harmonic, when that's achieved, it is when the wavelength is equal to the length of the tube. So a little bit different to the first one. The wavelength was equal to twice the length of the tube. So we're shortening our wavelength, which means we're going up in frequency. We're actually doubling the frequency. And finally, we're going to look at the third harmonic. I'm actually going to do my wave pattern on the right so that we can see how we set this up. And for the third harmonic, it's actually called a second overtone. So second harmonic above the fundamental. Again, we're going to have for an open-ended column. So it's open on both sides. We're going to start with this area of maximum displacement. And I'm going to go to my reference chart here. And I'm just going to pick that area of maximum displacement. So we're not going to choose the first harmonic, the second harmonic, and we're actually going to choose the third harmonic. So the pattern that we're going to see in the green that we're going to follow is going to be between these bubbles of maximum displacement where the air is free to travel. So the actual pattern is going to look like this. It's going to go down, up, and then down. Okay, please allowing for my sketchy drawing there. And when we sketch the opposite of this, it's going to look something like this. Now, the important thing to be able to realize here is, again, what is the relationship between the length and the wavelength? Well, it turns out that if we look at this green pattern here, where I'm tracing over in yellow, if we look at just that portion of the wavelength, we're looking at 1.5 times the wavelength. Can we rewrite this in terms of wavelength? Sure we can. The wavelength is equal to 2/3 the length of pipe. So we're shortening the wavelength each time. When we move up the harmonics, we're getting a shorter wavelength and a higher frequency because they're inversely proportional. So what we're seeing is, if you look at the yellow boxes, we see L is equal to a half wavelength, L is equal to a wavelength, L is equal to 3/2 wavelengths. So you can see it's increasing by a half a wavelength each time. There's a pattern there as we move up the harmonics for an open-ended column. So it's important that you understand that relationship between the length and the frequency. That will also give you a relationship between the length and the wavelength. And you also need to be able to draw that pattern as I've demonstrated. Final thing I'm going to do is just to look at an actual worked example. So our setup here is an air column open at both ends is 1 meter long. Okay, 1 meter long. If the speed of sound is 340 meters per second and resonance occurs, what are the two lowest resonant frequencies? Of course, so there we're looking for F0 and F1, or the fundamental frequency and the first overtone. Or we can call this one here the first harmonic and the second harmonic. So as per all good physics worked examples, we got to ask ourselves, what have we got and what can we get? So what we've got, I'm going to write down my givens, good standard practice. Velocity of the sound wave is 340 meters per second. And the length of the tube, and of course it is open at both ends, so it's an open air column, is equal to 1 0.00 meters. Okay. So what are we looking for? We're looking for the two lowest resonant frequencies. Okay. So for this one, we need to get the frequency and we have the velocity. We need to get the frequency and we have the velocity. So straight away we should be thinking about the wave equation where v is equal to f lambda. We have the velocity and we need to get the frequency. So if we can get our lambda, then we're going to be in business. So if we can get our wavelength, we'll be able to get the frequency. So how are we going to get the wavelength? Well, for an open-ended column, you can memorize this, of course, but I'm just going to go quickly and draw that first harmonic. So it should be open, open. Okay, and we already talked about how that is, the length is equal to a half a wavelength. Okay, so another way of writing this, if we want to get the wavelength is equal to 2L. And we know what L is, mercifully. So we have the wavelength is equal to twice 1 meter, which is the length of the tube. So the wavelength now is equal to 2 meters. Good. So now we've got our wavelength. We can simply go back to this equation here. V is equal to f lambda. And we're just going to rewrite that. And we're going to look for our frequency, which is V over lambda. And we're going to put that in over here. Frequency 0 is equal to 340 over the wavelength for that lowest fundamental frequency, which was 2.00 meters. And we're going to get 170 hertz. So that is the lowest resonant frequency. Now, the keen eagle-eyed amongst you would have noticed something when we were going through the harmonic patterns for the open-ended column, and that is that there's a relationship, a ratio between the harmonics for the wavelengths, and the wavelength each time was cut in half. And so what we're going to see is we're going to see that translated as the frequency, which should double. But let's actually go through it anyway. So we're going to set up our second pattern because we were asked for the two lowest. So let's do it the long way. Why not? We can learn a lot by doing things the long way sometimes. Okay, and of course we can do the second part here. When you are drawing these standing wave patterns in tubes, you do need to put in the dashed line. So my mistake for not doing that before. It is important that you're putting in the dashed line above as well. Okay, so if we go back to it, now our length is equal to the wavelength. We already know that our length of the tube is 1 meter. So our wavelength is now equal to 1 meter. So our wavelength, of course, if you notice, the wavelength has gone down, which means the frequency is going to go up. And if we write our frequency, we're going to have velocity over wavelength again. Now we're looking for F1, which is the first overtone. It is the second harmonic. And we're going to have 340 over 1 meter, which is 340 hertz. So we can see that the frequency has stepped up from 170 to 340. Now what that means is that for that open air tube, if you can get the air moving into the tube to vibrate at 170 times a second or 340 times a second, a resonance will be achieved, and that wave is going to vibrate with a bigger amplitude and a stronger sound, a more energetic sound. So I'm just going to leave you with one question. Just going back to that question at the very top. If we say resonance occurs, it's 1 meter long. I would like you to figure out what the third harmonic frequency is. So we've done harmonic frequency 1 and 2. So just as a little bit of practice, I would like you to draw the standing wave pattern for the third harmonic and also figure out what that third harmonic frequency is for the worked example.